In section 3.3, we will discuss arc length and curvature. Let's start with the arc length. The arc length is the measure of the length of a curve. To calculate the measure of the length of the curve, consider a smooth curve C with a defined vector function r of t equal to f of t I plus g of t j. And t lies within an interval a and b. And we are interested to calculate the length of the curve between a and b. And we can use this formula S, which is the arc length, equal to the integral from a to b of the magnitude of the derivative of the vector function with respect to t. So first you calculate the derivative of the vector function, then you find the magnitude of the derivative, then you integrate from a to b. This is the same formula for a vector function in 3D. Let's take an example. We have two vector functions and we want to calculate the arc length for these functions between 1 and 5 for the first vector function and 0 and 2 pi for the second vector function. Okay, now we will use this formula. So first of all, we need to calculate the derivative of r. The derivative of 3t minus 2 minus 2 is 3, and the derivative of 4t plus 5 is 4. So this is the derivative. Now we want to calculate the magnitude. The magnitude is equal to the square root of the square of the x component plus the square of the y component of the derivative. Now let's evaluate this one. 3 to the power of 2 is 9, and 4 to the power of 2 is 16. 16 plus 9 is 25. Radical 25 is 5. Now we want to integrate and integrate, yes, between 1 and 5. The integral of 5 is 5t, and replace these values in 5t. You will have 5 times 5, replace 5 in t, minus, replace 1 in t now, 5 times 1. So 5 times 5 is 25, minus 5, which is 20. This is the length of the arc for this function between 1 and 5. For the second vector function, we will use these. It's given not in linear combination form, in a component form. So this is the x component, this is the y component, and this is the z component. Let's do the derivative of this vector function. Doing the derivative will give you these components. Now, after doing the derivative, let's find the magnitude of the derivative. Square each component and then take the square root, and squaring the first term over here will give you this one. We used a minus b, all of that squared, which means that a squared minus 2ab plus b squared. In this case, we have a plus b, so we're gonna use the identity a plus b squared is equal to a squared plus 2ab plus b squared, and you will get this one, and 2 to the power of 2 is 4. Now, we can add cosine squared t with the sine squared t. This is it. Minus 2t sine t cosine t will cancel with the 2t sine t cosine t. They will give 0. And for this term over here and this term, factor out t squared, and you will have cosine squared t plus sine squared t. And then we have the remaining number plus 4. We're gonna write it here. This one is equal to 1. and this one is equal to 1. Add the numbers. 1 plus 4 is equal to 5, and 1 times t squared is t squared. Okay, now we can solve this integral using this identity integral. I wrote it here. You don't have to memorize it. Whenever you have some complicated integrals and you want to use an integral identity, I will give it to you in the problem, and it will be given. So the first one will be u squared, and the second number over here will be a squared. Let's apply the formula. The formula tells us the integral of this one of radical u squared plus a squared du is equal to u over 2, which means u is equal to t, because u squared is equal to t squared. So replace it. You will have, first of all, we will factor out 1 over 2. We will write it here. We factor it out. And what we have from the inside, we have u, which is t, plus times, excuse me, times radical u squared plus a squared. This is u squared plus a squared on the radical. Now for the second term, we have a squared. A squared is already 5. Look at here. A squared is already 5. And we have ln, absolute value of u, which is t, plus radical again t squared plus 5. We will write it here, plus 5. For definite integrals, we don't take the constant of integration. And the limits of integrations, we put them here, and you have to replace them in t and calculate, and make sure that your calculations will lead to 25.343. And this is the arc length between 0 and 2 pi. Now let's return to the helix introduced earlier in this chapter last week. Consider a vector valued function that describes a helix which can be written in this form. Don't memorize this one. A helix, the general equation of a helix can be written as this form, where r here and here represents the radius of the helix, h and h over here is the height, which means the distance between two consecutive turns, and n is the number of turns that the helix completes. T is between 0 and h, and this is three-dimensional because we have three components. Let's find the arc length now for this. The first thing we need to do is to do the derivative. So the derivative of the cosine is sine minus sine of this argument, the same argument. But outside, you need to do the derivative of the argument inside the cosine, which we will get rid of t, and the others are constant, 2 pi n over h. And we already have r in the equation. As for this one, the y component, we do the derivative of the sine, which will becomes cosine of this argument, and the cosine of this argument, and we do the derivative of the argument, where we will have 2 pi n over h, and r, again, we have it already here. Already we have r. And the derivative of t is equal to 1. Let's calculate the magnitude of r prime. The magnitude of r prime of t we need to square each component individually. So we will square the x component, the y component, and the z component, which is equal to 1, 1 squared. 1 to the power of 2 is 1. And let's square this term over here and this term over here. And we will factor out, since we have common, 2 pi n over r and 2 pi n, it's 2 pi n r over h, excuse me, and 2 pi n r over h. We will factor it out after squaring, and we will have inside sine squared plus cosine squared. Sine squared plus cosine squared is already equal to 1. So multiplying 1 with this constant over here, with this term over here, will give you the same term plus 1. Okay, now we need to integrate now between 0 and h. How to integrate this radical? This whole thing is constant. And whenever you integrate a constant, you will get a constant times the variable you're integrating with respect to, which is in this case ct. So the integration of a constant is the constant times the variable t. In this case, since this is a constant, we're gonna write the t, the variable t, multiplied by this whole constant. Now, replace h in t, you're gonna get h times this constant. And we will simplify this, because the square root of h squared, the square root of 1 over h squared is 1 over h. So we will, this denominator will move out, and h divided by h is 1, and you will get the radical of this numerator only. This is a very nice equation. So whenever you want to calculate the arc length, you just have to replace the number of turns, the radius of the helix, and the height of the helix, or the distance between two consecutive turns, and you will get the length of the arc. Arc length parameterization. We now have a formula for the arc length of a curve defined by a vector valued function. Let's examine the arc length function. We already dealt with the arc length. But what is a or an arc length function? The vector valued function represents the position of a particle in space as a function of time. So if we have a vector function r of t, this will give you the position of this vector function in space for a given path, because this vector function represents a path at a given point in space at a given t. You will have a vector function pointing at this point on the curve. The arc length function measures how far the particle travels as a function of time. The first one, the arc length, simply gives you the measure of the arc between two given points. Now, the arc length function will give you how far the particle travels. S of t measures the distance traveled as a function of time. S prime of t, if you do the derivative, it will give you the speed of the particle at a given time. So S is given by this formula. It is equal to the square root. We have seen this before. The square root of the square of each component of the derivative. So we used to do the derivative first of all. Then we take the magnitude and we integrate between a, but now we have t instead of b. So this is not a number. This is a variable. So you're gonna use the same equation, but instead of specifying if an upper limit b, an upper limit value, you're gonna specify an upper limit variable t. So in this case, you will get a function instead of having a value that shows you the length of the arc. To calculate the derivative to get the speed, the, it's the same formula because we're doing the derivative of s. So do the derivative with respect to t for s, and since this whole thing is the magnitude, we wrote again the magnitude. We know before from previous courses, whenever you're doing the derivative of the integral, you will get rid of the integral and have the integrand only. So if you're doing the derivative of, let's say, the integral of t dt, so these will, think about it in a way that these will cancel each other, the derivative of the integral, and then you're gonna get the result as t. So the derivative of this integral is r prime, the magnitude of r prime itself. And don't forget to put instead of u t. So this is the velocity. So if we have a smooth curve r of t, the arc length is always increasing. And since this is positive because this is the magnitude, we can say s prime of t is always positive because the magnitude of the derivative is always positive. A special case we will consider is whenever we have a curve r of t, and a special case states that if we have the magnitude equal to 1, this is a special case, the derivative of r and taking its magnitude and having it equal to 1, replacing this magnitude equal to 1, you have it here, and you integrate from a to t, you will get t minus a. And if you start, this is the initial point, and if you start the initial point from a equal to 0, so the arc length will always be represented by t. It's always equal to t. So if you have the value of t, this is a faster way to calculate the arc length only in case the magnitude is equal to 1. If the magnitude of this vector function is equal to 1, you can directly write the arc length is equal to t if it starts from a equal to 0. So if you're calculating the distance between 0 and let's say 3, so the arc length would, you can write that the arc length is equal to 3. Let's find an alternative parameterization. We discussed the parameterization in the previous lectures, and we will discuss it in a more few examples now. Recall that any vector valued function can be parameterized via a change of variables. Finding an alternative parameterization of a given curve is called arc length parameterization. So we're gonna change the variable of a vector function without changing the shape of the curve. We discussed this before. What does parameterization means? If you have a vector function, let's say it is in function of a variable t, we can change the variable from t, let's say to u, to another variable without changing the shape of the curve. Although when doing this process, when you change the variables, you're gonna change the equation itself. However, even if the equation has changed, the curve will remain the same. Let's take an example. We have a function, and now this is not a vector function, this is a real function. Um, uh, Maybe there's a mistake here. We should correct this one. This is a vector function because it's written in a component form. So this should has an arrow. This should have an arrow, and this one as well. This is the x component, and this is the y component. We have a function. So we have a circle here, and this circle is of radius r. This is given that the radius is equal to 3, and we know that this represents a circle of radius 3 between 0 and 2 pi. Now we can parameterize this one by writing cosine 40 and sine 40. Nothing changes. It will remain a circle. It will remain a circle of a radius 3. However, the speed that the vector is traveling through this circle will be faster in this case. We discussed this before when we said we have like a wave that goes from 0 to pi, okay, for the initial one, for that one, between 0 and 2 pi. Now, this vector function, the initial one, this one over here, will cover this one in 2 pi. If we reparameterize this one, the new parameterization cosine 4t will give you the same circle with the same radius, but it will cover it faster. It will finish the circulation of this vector around the whole circle faster. And to find it, all you have to do is we added 4 in the argument of the cosine, so we're gonna divide by 4 here and divide by 4 here. 0 divided by 4 is 0, and 2 pi divided by 4 is pi over 2. So this will finish it in pi over 2. So if this is pi, so pi over 2 is the quarter of 2 pi. So this is pi over 2. So this wave will look like, we'll finish it in this. It will have the same all characteristics except for the frequency. Let's take an example and reparameterize and change the variables from variable t to another variable u, as we're gonna see now. Okay, find the arc length parameterization for each of the following curves. Before, this was an example just to have an intuition what's happening visually to this process of this operation called parameterization. Now let's really change the variable and find a new equation that will represent the same curve, the same radius, for example, but of course, the time to finish this whole curve will be maybe more or less. Let's say, let's start with the first vector function. Find the arc length parameterization for each of the following curves. Let's start with part A. In part A, given that a vector function is equal to 4 cosine ti plus 4 sine t j for t greater or equal to 0. Let's apply the formula that we have, the same formula that for the arc length, but this is a function in function of t, and we're gonna write this in the upper limit for this integral. Let's find the magnitude of this vector function. The magnitude is given by the square root of the squaring of the x component plus the square of the y component. Now we have a common factor here, we can factor out 16 and we will get sine squared u plus cosine squared u equal to 1. And 1 times 16 is 16 and square root of 16 is 4. Okay, now integrating this one will give you 40, and this is the result. Initially, we said let u equal to t. We will do another change of variables in another examples. We're gonna see that. But in this one, starting with the simplest case, we're gonna say let u equal to t. So we just replace instead of t, u by u. And regarding this one, we also need to change this one, the condition, the constraint given on the vector function. This is given, always given with the vector function for t greater than 0. Now we have to reply, since s is equal to 40, we're gonna say t cross multiply t equal to s over 4. Now replace, instead of t, replace s divided by 4, and you will have this vector function with variable s. Initially, this was the vector function. As you can see, this is a circle with radius 4, but the argument changes. This is a different equation, but will give you the same circle, the same shape for this vector function, but of course, traversing the whole curve will be different from this one. Since t is equal to s over 4, we found it from here, replace t for s divided by 4, cross multiply, you will have the same condition for this one, s greater or equal to 0. For the second one, we have this, given this is our the derivative of the vector function. Let's go back and see it. The derivative of this one is 1. The derivative of the y component is 2. The derivative of 2t is 2. So the derivative of r is given by 1, 2, 2. Let's replace it. 1, 2, 2. And the magnitude is equal to, this is 1 plus 4 equal to 9. Square root of 9 is equal to 3. Evaluate this integral, you will get 3t minus 9. Let's change the variables now. S is equal to, this is s. S is equal to 3t minus 9. Now we need t. Rearrange and find, solve for t. T will be equal to s divided by 3 plus 3. Now replace this s in the initial function. This is the initial function. Now we found the new variable s, which is equal to t equal to s divided by 3 plus 3. Replace it in t over here, and t over here, and t over here. You will get this final result. Both this one and this one have the same shape, but let's see if the condition will change. What's the condition of the condition is t greater than or equal from than 3. So let's replace this one for t greater or equal than 3, as replace for t as equal divide by 3 plus 3 greater or equal to 3. This will cancel out and you get a 0 on the right side. Cross multiply and s will be greater or equal from 0 for this vector function in function of s. Let's discuss the curvature now. The concept of curvatures provide a way to measure how sharply smooth curve turns. A circle, this is a special case, where the curvature has a constant curvature. Look at these two circles. If you complete it, you will get a circle here. If you take this arc, you will realize that this arc, the curvature of this arc is different than the curvature of this arc. We say that for this circle, the small radius 1 has a high curvature. As the radius becomes smaller and smaller, the curvature will increase. This one, the bigger one, has a large radius but low curvature. So you can calculate how sharply a smooth curve turns. And this is called a curvature. And you can calculate this and get an exact number. And in this way, you can compare two curves. You can compare two curves by calculating their curvatures. To calculate the curvature, we're going to use this formula. Let's consider we have a curve C, and this is a vector function r of t, and the curvature will be denoted as kappa. The kappa of C at given t is given by this formula. The kappa is equal to the magnitude of the derivative of the tangent unit vector divided by the magnitude of the derivative of the vector function. If you have a 3D case, a curve in 3 dimensions, you're gonna use this equation. Kappa is equal to the magnitude of the cross product of r prime and r double prime divided by the magnitude of the derivative of r to the power of 3. Let's take an example to calculate the curvature of a curve. Before doing this in example 3.11, if you have a scalar function and not a vector function, a scalar function, or excuse me, a real function, not a vector function, you can calculate the curvature kappa at a given point xy by calculating the derivative of y prime, and the double derivative y double prime. And it is given by this equation, the absolute value of y double prime divided by 1 plus y prime squared, and all of that to the power of r divided by 2. In example 3.11, in part A, we are given a vector function r. In part B, this is a real function. So we're gonna use both different equations. We're gonna use this one, the kappa, for this equation, and for the part B, we're gonna use this one. Starting with the first equation, which represents a helix, you're gonna ask, this is a three-dimensional case, but why are we using this one instead of using the kappa of this of a three-dimensional case? Although helix a three-dimensional case, this can be simplified as a cylinder or a circle if you look at it from above. If you look at it from above, you're gonna see an XY plane. In two-dimensional case, it looks like a circle. And this symmetry allows us to use this equation. You can use this equation, no problem. You will get the same result, don't worry. For simplicity, we're gonna go ahead and use the first equation. The first equation is given by this one, so let's go ahead and start calculating t prime and then r prime and find their magnitudes and do the division to calculate kappa. First of all, let's calculate the tangent unit vector. The tangent unit vector is given by this formula, r prime of t divided by the magnitude of r prime. Let's do the derivative of r. The derivative of r is given by this one. We discussed how to do the derivative of the cosine and the sine, and the derivative of 3t is 3. And divide by the magnitude of r prime. So we have r prime, let's take the magnitude. Evaluating this one, we're gonna get this tangent unit vector. However, we want the derivative of the tangent unit vector. So let's do the derivative of this one. The derivative of the x component, the derivative of the sine t will give you cosine t. The derivative of the cosine t is minus sine t, and the derivative of a number is 0. Now we have the numerator for the kappa. We need to find the denominator. The denominator is already found, which is this one. This is the denominator. Just replace now the values and find the magnitude. Kappa will be equal to 4 over 5 divided by 5, which is equal to 4 divided by 5. This is the curvature of this vector function at t equal to 4 pi over 3. Just replace at the end the value of t, which is equal to 4 pi over 3, and calculate. You're gonna get the helix. And as you can see, the curvature of the helix is constant at all points on the helix. It will be the same because we have this nice symmetry in this structure of the helix. Now for the other one is given a real function, square root of 4x minus x squared. And if you plot this this function, you're gonna get a semicircle. Let's calculate the curvature of this semicircle. In this case, for a real valued function, we're gonna use this equation. Let's start calculating the derivatives of this function. The derivative of this is the initial function. This is the initial function. And let's write this square root in the form of power. It's easier when doing the derivatives. And when we have the derivative of u to a power of n, the derivative of this one, the formula states that this one is equal to n. We take the power, and the power becomes the coefficient, and then you subtract 1 from the power, and then you do the derivative of u. Let's apply this formula to do the derivative y prime. So first of all, the power is half. So the formula says take the power is half, times u, this is u, this is u, to the power, all of that to the power of the power minus 1. So half minus 1 is minus half, times u prime. So we do the derivative of u prime. Derivative of 4x is 4, minus the derivative of x squared is 2x. So to simplify this furthermore, we're gonna multiply half by this factor over here. So half times 4 is 2, and half times minus 2x is x. And we write this term again over here. So we calculated y prime. We need also y double prime. Y double prime is the derivative of this one. Again, we want to do the derivative of y prime of this one. Again, use this formula to calculate the derivative of this one. In addition to another formula, whenever we have u dot v prime, please try it out. U dot v prime, or the derivative of u dot v, will give you u prime v plus v prime u, v, v prime u. So this is u now, and this is all v. To do the derivative of these two factors, use this equation. And also this equation, because we have here a polynomial or a function raised to a power. So you also need this one as well. And after applying these two equations, you're gonna get y double prime, this whole thing over here. Let's apply the formula after finding y prime and y double prime. Y double prime lies on the numerator of the kappa, so we're gonna write this one over here. Oh, excuse me. So we solved this one. The result is y double prime is this one. Okay, and so we have, let's see, we have this one is y prime, and this one is y double prime. Okay, let's now replace them in the equation. This is y double prime, put it over here, and taking the absolute value of y double prime. And for y prime, we will replace this one over here in y prime and square it. Don't forget to square. Okay, so the negative sign will turn into positive because we have absolute value over here, and we're gonna square this whole term. Now, squaring the first one over here will give you 2 minus x, all of that squared. And we're gonna square minus half. If you have u to the power of m, all of that to the power of n, this, we know this identity of powers from powers. You will say that u is to the power of m times n. So 2 times half is minus 1. So 4x minus x squared to the power of minus 1 can be taken as the reciprocal of this one and becomes the denominator. Great. Now, we can say that this is 1 divided by 1, and we take the common denominator, so we can add this rational function with 1. And the common denominator is 4x minus x squared. So multiply 4x minus x squared times 1, you will get this one. And expand 2 minus x squared, you will get this one. We can further simplify 4x minus 4x and minus x squared and minus x squared, we're gonna get 4. Now, how to evaluate a divided by b divided by c divided by d? There's two ways to do that. You can multiply the parts of the fractions that are near to each other. You're gonna say b times c, and the ones that are farther away, a times d. So you will have a times d divided by b times c. This one of the ways, two ways, or you can take the denominator here of this fraction and take the reciprocal of this one. Okay, so if, in other words, this one denominator will become the numerator. Let's multiply these two fractions. This one can be simplified with this one, and 4 divided by 8 is 1 over 2. And this is the curvature of this semicircle, which is the reciprocal of its radius, since the radius here of this circle is 2. The kappa value is equal to 1 over 2, or the curvature is equal to 1 over 2 or 1 over the radius.